This is Physics 1020 and 1090. This is a lecture for Friday, April 10th. We're in Chapter 29 on nuclear physics. This is the second lecture from this day, and we're going to be talking about other types of radioactive decay. So first, a lightning review. There are three main types of radioactive decay: alpha, beta, gamma. Alpha decay is when the nucleus shoots out an alpha particle, which is the nucleus of a helium atom. So uranium-238 shoots out the alpha particle, becomes thorium-234, alpha decay. Another type of decay was beta decay, when the nucleus shoots out an electron. Thorium-234, one of its neutrons turned into a proton and shot out an electron in the process to balance charge. Thorium-234 became protactinium-234. Then the third one, which we haven't talked about yet, is gamma decay. And gamma decay is when you shoot out an electromagnetic wave. So let me show you an example of gamma decay. First, let's start with molybdenum-99. Molybdenum-99 does not decay by gamma decay. It's standard beta decayer. So it shoots out an electron. The number of neutron turns into electrons, so you go from 42 up to 43, which is technetium. And number 99 doesn't change. However, it decays to an excited state of technetium. That's what this M means. 99M means it's an excited state of the nucleus. Now remember when we talked about the Bohr atom, we talked about having different energy levels for the electrons surrounding the nucleus. And those energy levels could be in the ground state, the lowest energy state, or excited states. If they're in excited states, they could drop down to the ground state and release a photon. Well, the same thing here happens with nuclei. You go into an excited state of technetium-99 called technetium-99M, and then that technetium-99M can drop back down to technetium-99 and release a photon. In this case, it's usually a very short wavelength gamma ray photon. Now, usually these excited states don't last too long, but in this case, the excited state lasts 6 hours. And it releases a photon with a photon energy of 140 kiloelectron volts. Now, this happens to be very important in nuclear medicine because, first of all, this half-life is an ideal half-life for nuclear medicine because you have to have enough time to make the technetium-99M, get it to the patient, give it to the patient, do the medical imaging. 6 hours is about right. You don't want to have it too long because if you had it, say it was 6 days, then you'd give the patient the technetium-99. Some of the radiation would be used for medical imaging. Then they'd go home and they'd get a dose of radiation from the gamma rays, but wouldn't be contributing to image. You want to try to do imaging without dose. You don't want to give a dose when it's not contributing to image. So you don't want to have it too long, but you don't want to have it too short. 6 hours is just about ideal. Also, this photon energy, 140 keV, is also just about ideal. Number one, 140 keV or photons can pass through the body very nicely. So they can get out of the body and you can use them for imaging. Again, you don't want to create a photon that's just going to get absorbed by the body and doesn't contribute to the image. So if you're doing imaging, you want the photons to be able to get out of the body. They don't give a dose to the body. They give a contribution to the image. Also, a lot of photon detectors are optimized so that they work great right around a few hundred keV. So this is like the ideal isotope for nuclear medicine. The other thing you can do with technetium-99M is you can attach it to a lot of other molecules, and you can pick those molecules to be specifically absorbed by different parts of the body. So for instance, there's a type of molecule you can attach the technetium-99M to, and it'll be absorbed by the heart, and then you can give this radioactive element to a person, and then you can watch how it's uptake by the heart, and you can try to learn something about how the heart's functioning. So Technetium-99m, a great example of gamma decay and also a great example of use in nuclear medicine. The way it's usually done in nuclear medicine is you produce molybdenum-99 in nuclear reactors. You separate it, you send it to the hospital, and then it sits there in the hospital and decays slowly to technetium-99m. Then the interesting thing about technetium-99m is it's water soluble. So you can flush it out by flushing it out with saline, and then you get saline which contains technetium-99m separated from the molybdenum. You now have gotten rid of all your technetium-99m, but you can wait another day and it'll build up again as the molybdenum decays. Then you can flush it out. Sometimes they call this milking the generator. Milk it out, and you got more technetium to use in your imaging experiments. The next day you go back. And this works until slowly over several weeks the molybdenum will all decay away. Most gamma ray emitters have a much shorter lifetime than this. So you almost get, it's almost as if the gamma ray is given off in addition to an alpha or beta. But in this case, the gamma ray goes to a fairly long-living excited state. Okay, here's another example. Positron decay. Let's think back to your isotopes of carbon. Carbon-12 is stable, has just the right number of neutrons to be stable. We looked at carbon-14. It had too many neutrons. Carbon-14 with too many neutrons, so basically one of the neutrons turns into a proton, and it goes by beta decay, beta minus decay, to nitrogen-14. What happens if the nucleus contains too few neutrons, say carbon-11? Carbon-11 wants to get more neutrons. So what happens is one of the protons turns into a neutron. If one of the protons turns into a neutron, you go down from element 6, carbon, to element 5, boron. The number of total protons and neutrons doesn't change, but you now have what used to have 6 positive charges, now has 5 positive charges. Where does the other charge go? It gets emitted as a positron. A positron is a positive electron. It's an example of antimatter. So, these were positive electrons, or positrons, were discovered in 1932. And keep your eye on 1932. That's going to be a big year for nuclear physics. We're going to see a lot of things happen in 1932. But you can emit the positive electron, an example of antimatter, and we often call this a positron. And this type of decay is often called beta plus decay, as opposed to beta minus. So there's really two types of beta decays, beta plus and beta minus. Which one happens depends on whether you're neutron rich or neutron poor. Again, we put a 0 and a +1 on the positron just to make the bookkeeping work out. Now, what happens? What's the fate of this positron? Well, positrons will almost immediately interact with an electron and annihilate each other. Positron's a form of antimatter. All particles have their antimatter particles. Antimatter is usually very rare, but if you get an antimatter particle produced and it meets its particle, normal particle, it will annihilate and give off photons. So what happens here is you have a carbon-11 decays by positron decay, shoots out a positron, which will then go interact with an electron and give off photons. Half-life for this is about 20 minutes. So this is also used in medical imaging. Here's another example of positron decay. You do this one. Fluorine-18. You might think fluorine-18 looks like it ought to be stable. 9 neutrons, 9 protons. But remember, as elements get heavier, you tend to need more neutrons. So this is actually neutron poor. It would like to have more neutrons than 9. So what happens is the fluorine decays. It's unstable. Decays by positron decay to what? Stop the video. Figure it out. It's going to decay. It's going to change from 1 of the protons is going to turn into a neutron to give more neutrons. So you go down to 8. Element 8 is oxygen. This is oxygen 18, which is stable. and it gives off the positron. And the half-life for this is 109 minutes. And the half-life is very good for medical imaging. You can produce the fluorine-18, and then you have over an hour to get it to the patient, do the medical image, but then it will decay away over the next few hours, and it won't be contributing to dose for weeks to come. This is used in what's called positron emission tomography. That is, you can attach this fluorine-18 to various molecules. It will go to spots in the body. It will release its positrons, which will annihilate with an electron, give off a photon, which you then detect with a photon detector, and you can do images and figure out where the fluorine-18 was. For instance, oftentimes fluorine-18 is attached to a type of glucose, but not normal glucose, a special type of glucose. Remember, glucose is used by your body to create metabolic energy. So this fluorine-18 attached to this special type of glucose will go taken up by cells that are metabolically active, but because it's not normal glucose, it gets trapped there, and it'll just sit there, and it'll release its positrons, and it'll give you a signal. So this fluorine-18 attached to this type of glucose will often be used in brain studies where you are doing some task and you want to find out what areas of the brain are active. You give the person glucose with fluorine-18 attached. You then let the person do the task. You find out where the fluorine-18 goes in the brain. Those are the active areas, and you can make images of that using positron emission tomography. So positrons can be useful. They're always going to be found when you have neutron poor isotopes decaying. Here's another type of decay called electron capture. Now, let's remember there's two types of I want to talk about isotopes of iodine. We've already talked about iodine 131. Iodine 131 did a normal beta decay, beta minus decay. It went to xenon 131, and it gave off a electron, minus electron, so a normal electron, and that's what can do the damage to treat thyroid cancer. Also, which we didn't mention before because we hadn't talked about gamma decay yet, is it usually also gives off some gamma decay. You often get gamma decays given off in addition to either alpha or beta decays. So this is actually very useful for thyroid cancer, not just because you have the beta to kill the cancer cells, but you have a gamma to do some medical imaging with. But let's consider now another isotope of iodine, iodine 125. Now, iodine 131 had too many neutrons, so it decayed by beta decay. Iodine 125 doesn't have enough neutrons, so you might think, would decay by positron decay. But there's a competing process to positron decay called electron capture. What happens is an electron in one of the inner shells of the atom, of these electrons going around the nucleus, gets captured by the nucleus itself, goes into the nucleus, and changes one proton to a neutron. The positive proton combines with the negative electron, becomes a neutron. So what you have in this case is iodine 125 goes to electron capture to tellurium 125. Element 53 goes to element 52. Well, let's think about this for a second. If you capture one of those inner shell electrons, you now have an open spot, open hole in your inner electron orbit. You can have an electron that will drop from an outer orbit down to the inner orbit. If this was in the Bohr model for hydrogen, you now expect that to release its energy, which it loses, as a photon. But there's a competing mechanism. There's always competing mechanisms. This is what makes nuclear physics so interesting. You can also have the energy that's given up when this electron falls down into the hole, which is produced by electron capture, and it can give it to an electron. And the electron can go flying out of the atom, and it's what's called an Auger electron. And you see now, if this electron falls down into this hole, that leaves a hole right here. And another electron can fall into that hole and give its energy to another electron, which leaves the atom. And what you can get is a whole cascade of electrons. Iodine 125 often releases like 21 electrons. Now you can't just create energy, so these electrons tend to be fairly low energy electrons. Enough energy to do damage, but such small amount of energy that they don't move very far. And this is another way you could apply iodine to attack, say, thyroid cancer. I like to compare iodine 131 and 125 to the difference between a rifle and a shotgun. Iodine 131 gives off one bullet, the electron, which shoots out and can travel a long ways and do a lot of damage. Iodine 125, on the other hand, will produce a cascade of low-energy Auger electrons. And these low-energy Auger electrons are like shot from a shotgun. It can do a lot of damage spread out over a big distance, but it doesn't travel too far. So a shotgun approach sometimes that can be effective. It won't produce much damage a long ways away from the iodine, but it will produce a tremendous amount of damage close by. Just like a shotgun will produce a tremendous amount of damage nearby, but if you want to shoot a guy 100 yards away, you better use a rifle. Now, Auger electrons and these cascade processes were discovered in part by a scientist by the name of Auger, but also independently by Lisa Meitner from Austria. And we're going to run into Lisa Meitner again when we discuss nuclear fission, but I wanted you to realize this was one of her earlier contributions to physics, analyzing Auger electrons. One last topic for today, and this isn't a radioactive decay at all, so it doesn't really belong in this lecture, but it's an oddball thing I wanted to talk about, so I thought I'd tack it on here. And this is deuterium. Deuterium is a stable isotope. It's an isotope of hydrogen, but instead of having a hydrogen 1, which would just be a proton, it's hydrogen 2, which is a proton and a neutron combined together. So the nucleus of H2 is actually twice the mass of nucleus H1. So it's a big difference in mass percentage-wise. This is often called deuterium. Sometimes it's even given its own symbol, D instead of H. Usually these mean exactly the same thing. It's just that this is such a unique case that is sometimes given its own symbol. 99.99% of the hydrogen on Earth is normal hydrogen. Only 0.01% is deuterium. Still, what's the oceans full of? It's full of water, which is H2O, so it's two hydrogens. So even if only 0.01% of those hydrogens are deuterium, there's still a lot of deuterium out there in the ocean. Now, if you made water out of normal hydrogen, the molecule as a whole would have an atomic weight of 18. 16 from the typical isotope of oxygen, and 1 each from the typical isotope of hydrogen to give you 18. But sometimes you can make water out of deuterium, and then it's D2O, and then it's 16 from the oxygen and 2 each from the deuterium, so you end up with a weight of 20. Well, that's a pretty big difference, 18 to 20. That's 10% difference in the atomic weight of a very common molecule, water. So heavy water can be produced just like normal water. Now, heavy water has 10% larger mass. That's not enough to cause any big problems. You could drink a glass of heavy water and no problem would occur. But nevertheless, it's a big enough difference that heavy water has some uses, and we're going to see one particular use when we're talking about nuclear reactors. So we've now talked about a variety of types of nuclear decay. Oh, by the way, before I summarize at the end, deuterium was discovered in, you guessed it, 1932. Big year for nuclear physics. So now we've discovered a lot of different types of nuclear decays, most of them naturally occurring. Next class, we're going to move on and talk about nuclear reactions, a lot of these man-made reactions that are important in the history of nuclear physics.